All right, so the first thing that I want to do today is remind you all that you have an exam Wednesday evening. So just to be very, very clear, your exam is Wednesday. I believe it is at 6 p.m. And I believe we have room 108 in IESB reserve, but I will send out an email to everybody today confirming that time and location. So it's definitely Monday evening. It's definitely somewhere in the IESB because that's the only place large enough to fit both sections at the same time. But the specifics I'm not 100% on. I believe it's 6 p.m. and I believe it's 108. I'll get that certified today. All right, so today we are junction transistor. All righty. So way back in late 1947, shortly after World War II concluded and the Cold War with Russia had just began, engineers at Bell Labs were trying to create a replacement for vacuum tube technology because most vacuum tubes were made in the USSR, and we effectively had an embargo with it. So we were trying to develop an electronic device that would replicate the behavior of a vacuum tube. And in late 1947, a couple of engineers at Bell Labs, William Shockley and John Bardeen, and one other guy whose name I can't remember because he didn't win the Nobel Prize for it for some reason, developed the bipolar junction transistor, okay? So a bipolar junction transistor, yeah, for everybody in Zoom, go ahead and type something in chat so that I know you're here. Thanks, and I'll get back to it. All right, so a bipolar junction transistor is an electronic device in which holes and electrons, that's why it's bipolar, because it uses both charge carriers, in a what we'll call sandwiched PN junction configuration. So there are two different types of bipolar junction transistors. We're going to focus the overwhelming majority of our talk on the first one, which is called the NPN transistor. Just making sure. All right. So this drawing is not remotely to scale, and I'll explain what I mean by that in a moment. So here we would have a neutral N region. And then we have a PN junction. So here we have a neutral P region. And then again, we have down at the bottom a neutral N region. So we have a sandwich where it's an N region on both sides of a P region. Now, PN junctions are not symmetrical devices, meaning that there are different dopant concentrations across each region. So we are going to call the region at the top, which has the lightest doping concentration, the collector. So it's going to have a terminal here, C, that stands for collector. And we may observe when it's connected to something, some current IC flowing into that terminal. That's called the collector current. Our neutral P region is going to be more heavily doped than our collector N region, okay? We're going to call this middle region the base. And so there is a terminal here with a B for the base, and there may be also some base current IB. And then lastly, down here, we have an extremely heavily doped N region. So I'm putting 2 pluses on it. So that's letting us know that this region at the bottom, which we're going to call the emitter, is more heavily doped than the base, which is more heavily doped than the collector. So one other thing here, we're going to have our emitter terminal, and here is our emitter current. So here we have what's called the collector base, or usually more base collector BC junction. It's good old regular PN junction. And here we have the second PN junction, that is the base emitter junction. So this is structurally what it looks like. And when it's unbiased, there will be depletion regions and all that kind of stuff that are behaving exactly how we would expect them to behave if we treated it as just 2 separate PN junctions. We represent this guy with the following schematic symbol. Here's our collector. Here's our emitter. Here's our base. And so we're going to define some voltages. Let me put the currents on here first, though. So here's my collector current. Here's my emitter current. Here's my base current. The potential difference between the collector and the base, we're going to call VCB. So it's simple double subscript notation, where the first subscript is the positive polarity terminal, the second subscript is the negative polarity terminal. That then gives us here between the base and the emitter, VBE, and finally between the collector and the emitter, VCE. And notice on this particular guy, this is for what's called an NPN BJT. The arrow is pointing out. Okay? When we discuss PNP BJTs, the arrow here is pointing in because the base current flows in the opposite direction. That's all that really means. All right. So in a BJT, and this is true for both NPN and PNP, to be clear here, the emitter region, very heavily doped, as this region is where the majority, so not all, but the majority of charge carriers come from for current conduction. All right. So it is extremely important that the emitter region is more heavily doped than the other two. The base is doped less heavily than the emitter. And this terminal is used to control the flow of charge carriers from the emitter to the collector. So we're using, so there's two different ways to interpret this. Okay? We can either treat this device as a whole as a current-controlled current source, meaning that the value of our base current winds up controlling the amount of current that flows, or the amount of charge carrier movement from emitter to collector. Or we can think of it as a voltage-controlled current source, because in order to get that base current to flow, we have to apply some potential difference between the base and the emitter. So all of the transistors that we're going to be dealing with in this class, both BJTs and CMOSs, CMOS transistors, can all be thought of as dependent current sources. It's just really how you interpret things as to whether you consider them to be a current-controlled current source or a voltage-controlled voltage source. This textbook that we're using specifically uses a voltage-controlled current source model, so that's what we're going to be going with, but I wanted to talk about that a little bit. So the base terminal, whether it's the current flowing through it or the voltage applied to it, is what's controlling everything else, and we'll see that in a minute. All right, so there is another note that we need to make. The base region is very thin. Less than the diffusion length of the minority charge carriers. And it's made this thin to prevent excessive recombination in the base. We'll talk about that shortly as well. Lastly, we have the collector. The collector is lightly doped in comparison to the base, such that under reverse bias, a large electric field is sustained across the base collector junction, which sweeps. So we're going to have, to some extent, minority carrier extraction occurring. Towards the collector terminal. All right. Okay, so in a nutshell, then, what we have is an emitter, which in an NPN transistor supplies a whole bunch of electrons. And we have a base, which is supplying holes into the mix as well. And then we have a collector, which winds up collecting most of the electrons, and that's what's responsible for current flow through this device. But those conditions are, the current that's flowing are all dependent on the terminal voltages that we apply. So I want to make a simple table here. And this is all valid for an NPN transistor specifically. So let's say we put applied voltages here. Junction bias here. We're going to be looking at both the base emitter junction and the base collector junction, and then finally the operational mode will be our last thing. Oops, that looks like crap. Table so that we can read it. We know what goes with what. All right, so the most commonly used mode is going to happen when we have the voltage applied at the emitter is less than the voltage applied at the base, is less than the voltage applied at the collector. In this case, the base emitter junction is forward biased and the base collector junction is reverse biased. This is what's called the forward active mode. And we will see that when we are in the forward active mode, our transistor actually acts as a small signal amplifier, something that we're going to spend a lot of time talking about. When the emitter voltage is less than the base voltage, but the base voltage is greater than the collector voltage, both of our junctions are forward biased, and this is operation in the saturation region. When the emitter voltage is greater than the base voltage and the base voltage is less than the collector voltage, both junctions are reverse biased. This is known as the cutoff region of operation. And so saturation and cutoff allow a BJT transistor to be used to form digital logic. Saturation effectively is on and at a specific value, and cutoff is off, so that zero current flows through. So we can have digital logic using BJTs. And then lastly, we have the condition where our emitter voltage VE is greater than VB is greater than VC, which puts the base emitter junction reverse biased and the base collector junction forward biased. And we call this the reverse active region or mode. So I'll call it mode, because I used mode earlier. So what we're going to be doing for the rest of today's class is talking about how the device behaves in the forward active mode. This is effectively the exact same thing as what's happening in the reverse active mode, except that we'll find that the transistor is significantly less efficient at doing what it does when it's in the reverse active mode. So in the reverse active mode, effectively, we're making the collector the emitter, and it doesn't have a whole heck of a lot of electrons to be able to emit or inject into the rest of the device because it's much more lightly doped. So for those of you who did your freshman engineering here, how many of you guys remember using a BJT or a transistor at all? It happened to be a BJT in your water pump circuit. So if you put your transistor in and connected it backwards, it still worked. It just got really, really hot. This is why, because it's an asymmetrical device, okay? So you can still get those same currents out of it, but because it's trying to pull more electrons that can be supplied, the temperature has to increase in order to thermally generate those electrons. Causes it to run really, really, really hot. So we're going to focus today on forward active with the understanding that reverse active is effectively the same thing. It just does it more crappily. All right. So forward active mode operation for a Npn BJT. I'm going to draw a picture here. Still not particularly to scale, but we'll use it. So here is our base emitter junction. I'm drawing the base region smaller in physical size so that we'll remember that it's thinner. Here is the base, sorry, this is base collector. And this guy down here is the emitter. My apologies. So this region is very heavily doped. This region is heavily doped. This region is lightly doped. And to be clear here, here's our collector. Here's our base. Down here is our emitter. And For the forward active region, we're going to apply some voltage where VCB is greater than VBE. And we're also going to have our base emitter voltage here, VBE, and let's just say, to be explicit here, is greater than 0. All right. So this is what forward active operation is going to look like. So let's take a quick second here. Notice we have 2 PN junctions. All right. So how is the base emitter junction biased? Positive polarity terminal of the voltage VBE is connected to the base, and the negative polarity terminal is connected to the emitter. So that means that the base emitter junction is forward biased, all right? So we are going to have, let's see, a very thin layer of bound negative charge and an even thinner layer, but it's hard to draw it even thinner, of bound, I can't spell today, positive charge here. And the electric field of the base emitter junction, actually I'm going to say, I'm going to call it EB. The reason is because it's directed from the emitter to the base, because the positive charge is on the emitter side, is going to be reduced by the forward bias voltage. So we're going to see that we have a relatively small electric field oriented in the up direction in this drawing. Okay. For the base collector junction, the N side is at a higher potential than the P side, which means we have reverse bias conditions. So that means that we are going to have a relatively thin bit of bound charge here. So this is bound to negative charge again. We're going to have a large region of bound positive charge. The depletion region here is much larger because the dopant levels are much lower. And this is going to give us an electric field directed from the collector to the base. And it's going to be larger. Because we're under reverse bias conditions. So we have a very large electric field oriented down because of the biasing conditions of this junction. Okay. All right, so electrons. Let's talk about what's happening in our forward bias junction first. Okay. So under forward bias conditions, our barrier potential is decreased, which means the probability of diffusion of minority charge carriers. So effectively, we should expect to see electrons can diffuse from the emitter into the base region. And we should also see that holes can diffuse from the base into the emitter. So electron diffusion is going to look something like this. We have a whole bunch of electrons diffusing into the base region. And then we should see that holes are diffusing into the emitter. So as a starting point here, we could say that the emitter current should be something like let me see here. So acceptor atoms. So I'm going to call this NB for, because it's the donors in the base region. And this NE is the emitter dopant concentration. Okay. So this is our base. This is just an educated guess, really, as to how this thing is going to at least partially behave. We have a forward bias PN junction, so it stands to reason that the current flowing in that region is going to behave like we expect a forward bias PN junction to do, right? Nothing too wild or crazy there, right? We have holes diffusing over, and we're also seeing that holes wind up being resupplied by the base, which means this gives us a base current in this direction. And since we have holes traveling down and electrons traveling up, that gives us a net positive current, IE, in the down direction as well. Now, some of the electrons that have diffused into the base region are going to wind up recombining with holes. The amount is very small, and it effectively determines the efficiency of our device, which we'll talk about momentarily. So we can say some of these guys are going to wind up recombining, and so not all of our electrons that diffused across the forward bias junction will wind up getting swept through into the collector region, right? So this large electric field here electrons move in the opposite direction of the applied field. So when the electrons diffuse through here, they're effectively going to see a very low concentration level here, means they're diffusing towards this region, and then the electric field pushes them through towards the collector. So we're going to have some collector current, IC, like so. We also have a little bit of contribution from holes to the recombination current there as well. So these are the different mechanisms that are happening. All right, so our collector current, IC, is going to be smaller than the emitter current by definition. And the reason for that is that the collector current does not have a hole flow contribution as well, right? So any holes are going to get pushed away. So we shouldn't see holes traveling up, canceling out any portion of our current, right? So all of the holes, if any hole in this region is going to get pushed away from that junction, only electrons flow through. So we can say that our collector current, we're going to have a very similar expression, but there's a couple of key things here, is going to be given by, oh, sorry, and I forgot to do this part right here. This should have been EXP. Let's see, I'm just going to call it VF over VT minus 1. Sorry, this was the coefficient which represented the reverse bias saturation current, and then it's multiplied by that same exponential bit, just like it was in the forward bias junctions earlier. My apologies for forgetting that bit. All right, so IC is going to be, and there's a derivation in the textbook that's lengthy and very, very similar to exactly what we did for PN junction, so I'm not going to bother with it. dN Ni squared divided by NB times WB where this guy right here is IS. So this IS is effectively taking the role of the reverse bias saturation current in our BJT transistor. And the biggest thing that I want to point out here is that it's based purely on electron flow in this case. And instead of being dependent on the diffusion length of the charge carrier, it's dependent on the width or the thickness of the base region. And this goes back to that point where the base is actually much smaller than the diffusion length itself. So we are saying, effectively, we should see a lot less recombination because we're using a smaller value here. So the overwhelming majority of electrons make it through, and we're left with this expression, which is telling us really how this thing behaves, under the assumption that VBE is much greater than VT, which it should be in the overwhelming majority. So that's why we're getting rid of this -1 bit right here. All right, so we can actually express all of the remaining currents in terms of IC, okay? So what I mean by that is, if we look at our simple diode equation here, the number of electrons and the number of holes that cross that junction are related to each other. They're both constant values depending on the dopant concentration and the diffusion lengths and the diffusion coefficients, right? So for every, let's say, 100 electrons that goes through, there's a fixed number of holes that go through as well. And so we can express this relationship as a simple fractional rule. So in a bipolar junction transistor, the base current, IB, is simply 1 over beta, which we'll talk about in a moment, times IC, or we can express it as, 1 minus alpha times the emitter current. Where beta is known as the common emitter current gain, and is defined as beta is simply equal to the ratio of IC over IB. Sorry, that should be B, and I want to make it clear that it's a B and not a beta. So this coefficient describes how efficiently the transistor turns a base current into a collector current, right? So the larger that beta is, the better of a job of the transistor does in converting that controlling current, the base current, into the output current, which is the current flowing through the collector. Let's see, beta, I gotta leave myself some room here. Typically ranges from on the order of 10 to 100, could be higher, might be a little less. High power applications is typically a little bit less than this range, but typically speaking, somewhere in the 10 to 100 range is reasonable. If you go onto a data sheet for a BJT transistor, you're never explicitly told beta. What you get is what's called HFE. This is the exact same thing. This is the common emitter current gain, and the F stands for the forward active region, and the E lets you know that it's the emitter current gain. Okay? So on a data sheet, it doesn't say beta is equal to something. It says HFE is equal to something because the H parameter is what's more commonly used in industry, but it literally represents the exact same thing, the common emitter current gain. Just wanted to make a note of that. Let's see. And alpha is known as the common base current gain. And is defined as alpha is equal to IC divided by IE. So this tells us what fraction of the emitter current makes it through to the collector, or vice versa. Alpha typically ranges from 0.9 to 0.999. So it's always going to be some number less than 1. And the better the BJT operates, the closer and closer it is to 1. We can also express alpha in terms of beta. So alpha is simply beta over beta plus 1. And transversely, beta is simply alpha over 1 minus alpha. So if we know one, we know the other. That's why you don't typically see alpha on the data sheets. It's always beta or HFE. So from these different definitions, our operational equations are our collector current is IS times EXP VBE over VT. I want you guys, we're not going to go into great depth here, but this equation explains the amplification behavior pretty succinctly, right? For a very small change in VBE, we should see an appreciable change in the current because there's an exponential relationship between the voltage and current. So we can significantly amplify large voltage signals and turn them into, or small voltage signals and turn them into macro scale current signals by using a transistor. Our emitter current, IE, is 1 over alpha times IC, so that's going to give us IS EXP VBE over VT, which is the same thing as beta plus 1 over beta IS EXP VBE over VT. And finally, our base current, IB, is 1 over beta times IC, which is the same as 1 minus alpha over alpha IS. So these are the equations that govern the behavior of an NPN transistor in the forward active region. Just as a quick aside, these are also the exact same equations that govern the behavior of a PNP transistor, except instead of having VBE, we have VEB. Or you just put a negative sign on the voltage and it gives you the exact same thing. How they work is identical, except holes replace electrons. That's about it. All right, so we got a couple of minutes left in class, so let's work a few example problems. So let's see. There's one in the textbook that I like, but it's so wildly close to one of your homework problems, I'm kind of hesitant to do it because it just straight up pretty much gives you the answer. So if we might revisit that in a second. Let's take a look at one that's maybe a little bit more difficult, actually. So let's say that we have the following circuit. So we have one BJT transistor, let's call it Q1, and it is going to be connected to a second BJT transistor like so. We're told specifically that we have 5 volts applied at the collector terminal of transistor Q2. And we're told that we have 1 milliamp flowing into this node. Here is our base current IB1. Here is our collector current IC1. Here's a base current IB2. Here's a collector current IC2. And then we're not going to bother with the emitter currents in this one, because if we know the base current and we know the collector current, the base current plus the collector current gives us the emitter current, Kirchhoff's current law. So nothing wild or crazy there. We are told that transistor Q1 and the transistor Q2 are identical, meaning they have the exact same dopant concentrations, they have the exact same size, they also have the exact same current IS, which is going to be 10 femtoamperes. So that's 10 times 10 to the negative 15 amps for those of you who weren't sure what a femto was. Let's see, beta for both of these is 100. And lastly, we're told that our temperature is 300 degrees Kelvin, which means our thermal voltage VT is 26 millivolts. Our goal is to determine VBE and our collector current IC2. All right. So, does anyone have any thoughts whatsoever on how we might approach this? Start coming up with something. I recognize that this is your first ever transistor problem, so any idea is a good idea as far as I'm concerned at this point. So 5 volts is applied at the collector terminal of Q2. So that means that for transistor 2, VCE is 5 volts. But that's based on the equations that we have, where everything is based on VBE, VCE doesn't really help us. In fact, we could obviously see then, just from what we've talked about, that the amount of current that's flowing through the collector does not depend on the voltage applied at the collector terminal, as long as that collector base junction remains reverse biased, the current is independent of voltage. So just a quick aside. So let me ask you guys a question here. Does anyone else notice that the voltage VBE is the same for both transistors Q1 and Q2? Right? So the negative polarity terminal for the voltage VBE is ground. The positive polarity terminal for the voltage VBE is this node that's connected to the base terminal of Q2, and the base terminal of Q2 is also connected to the base terminal of Q1. So VBE, VBE for Q2 are the same. What does this mean, or what does this imply for the collector currents? So we know that the collector current for a transistor, IC, is equal to IS times EXP VBE over VT, which means IC1 has to be equal to IC2, since VBE is common between both transistors. Everybody okay with that? All right, so that's a pretty important revelation here. So if we can figure out what IC1 is or something like that, we can probably figure out IC2 pretty easily because they're the same thing. let's look at this node. All right, it's all one big node. If we apply Kirchhoff's current law here, we know that 1 milliamp is equal to our base current IB1 plus our collector current IC1 plus our base current IB2, right? Just good old Kirchhoff's current law, nothing particularly fancy there. We know that IC1 is, by definition, beta IB1, right? So let's go back here just real quick. So from how beta is defined, beta times IB is exactly equal to IC. So beta tells us the amplification factor here. So we can simply substitute IC1 as beta times IB1. And I know this is going to seem a little bit weird, but IB2 is then 1 over beta IC2, where IC2 is equal to beta times IB1. And that's because IC2 is exactly equal to IC1, and IC1 is equal to beta times IB1. So that means this beta, so if we're substituting it in, beta multiplied by 1 over beta, that just gives us IB1. And so what we're left with is 2 plus beta times IB1 is equal to 1 milliamp. So anybody have any questions, comments, concerns about the math and logic effectively that I use there to come to that realization? So I have effectively mathematically shown that the base currents, if the collector currents are the same, the base currents have to be the same as well, because the base current is related to the collector current by a factor of beta. I just wanted to be explicit in that. So I can solve this then and find that IB1, which is the same as IB2, is simply 1 milliamp divided by 2 plus beta, which gives me 9.804 microamps. Nothing wild or crazy there. And from this, IC1, which is the same thing as IC2, is simply beta IB1 is 0.980 milliamps, multiplied by 100. So now that we know what IC1 and IC2 are, we should be easily able to back calculate what VBE must be in order for this to occur. So VBE is going to be simply VT times the natural log of IC over IS. And I can get that by manipulating this guy, right? So if I divide both sides by IS, take the natural log, and then multiply through by VT, I'm left with VBE on one side. If I put in my numbers here, this gives me 0.658 volts. This configuration is what's called a current mirror. And so we see that whatever current is flowing through the collector of Q2 winds up flowing, that same current must flow through the collector of Q1, and we could actually hook up more and more. That's a fundamental building block of making large-scale amplifiers with BJT, which is something we'll get to later, but we're kind of introducing at least a little bit how it works now. All right, how did you guys feel about that problem?
Mostly with everything, after the initial assumption, everything makes sense.
Okay. So how did I know that VBE is the same for both? So the negative terminal here is attached to the ground. Crap, I didn't want to do that. And this ground. So they definitely share that common terminal, right? The positive polarity terminal, let me do it in pink. No, that's purple, whatever. Let me make it larger. So this is the positive polarity terminal, right? Which is connected by a wire all the way to there. So therefore, the positive polarity terminal is also shared. So I did make an assumption that VBE was the same. We can, by inspection, it's true. And once you can recognize that, then everything else follows pretty straightforward, I think. Any other questions, comments, concerns on this one? This is probably one of the harder style problems, at least we could do on this stuff before we start throwing in resistors and all that kind of jazz and start actually making amplifier circuits. All right, so let's do one more fairly easy one, at least in my opinion and in comparison to that one. And then we'll call it a day. So we have 15 volts. Here's a 10 kilo ohm resistor. Here's another positive 15 volts. Here's a 680 kilo ohm resistor. And we are told that the output voltage here, which is the same as the collector voltage, VC, is 7 volts. And we're also told that VBE is equal to 0.7 volts. I want to determine alpha and beta. Anybody have any ideas how I might go about doing that? So one thing, nobody's saying much of anything, we can go back to our fundamental definitions, right? So beta is defined as IC over IB, right? Once we know beta, we can get alpha pretty easily because alpha is simply beta over beta plus 1. How could we determine IC? Sorry, what was that? Yeah, the voltage drop over the resistor, which is just going to be what? 15 minus 7. How do we find IB? Yeah, the voltage over that resistor, which is going to be 15 minus 0.7. Nothing remotely hard about this, right? Just good old Ohm's law. This comes out to be 21.029 microamps, which gives us a beta of 38.042. And in turn, alpha, which is beta over beta plus 1, is 0.97. I showed you guys this problem specifically because I don't want you to get intimidated by these things, because simple rules like Kirchhoff's voltage law and Ohm's law and all that stuff still totally apply to all of this stuff. That's one of the places where I mean, this is my first time ever teaching this class at an undergraduate level, but that's where I saw most of the graduate students that I taught this stuff to a couple of years back suffered, was that they get so bogged down in all these pesky equations for how these things work, they'd forget that KVL and KCL and things like that have to also work all the time too, because they represent the fundamental laws of physics in the circuit realm, right? Kirchhoff's voltage law is the law of conservation of energy. Kirchhoff's current law is the law of conservation of charge. Those things have to be maintained at all times. All right, so that's really all I have prepared for today. We could take a look at the web work real quick if you wanted to and see how far we could get based on what we know today. This web work assignment, I believe, doesn't get assigned to you until Wednesday for whatever reason.
Doctor, when is the date for exam number 1?
It is Wednesday, January the 6th. So 2 days from today. It will be an evening test. In the ISB, I will send that the specific information regarding that out today, as well as the equation sheet that you will be allowed to use. It'll be attached to the test, but I want you guys to have it so that you can look at it and all that kind of good stuff too, and understand what's there. So maybe think about things that that may not be on there that you may need, although in my opinion, it's too thorough. Yes. So let's talk about the test real quick. There is going to be a multiple choice section at the beginning that is just purely theory questions, no calculations or anything like that. Dr. Batari and I have not yet settled on the number of questions that are there, but my guess would be it's either going to be 5 or 10, okay? Then there are going to be several questions regarding calculations. And the way that I have it set up is, it's effectively going through the material just how we went through it in the class. So the first question would be on drift current and diffusion current. And then the second question is on, so it's like drift current, diffusion current. There's one on, let me see, drift current, diffusion current. Built-in voltage and intrinsic carrier concentration. So I don't think you guys had to use the intrinsic carrier concentration equation that's given to you. I could have sworn it was given to, maybe if I looked at homework set number 1. Let me see something real quick. I thought it was on here, but maybe it is. Well, there's an intrinsic carrier concentration equation. So instead of just saying the value is this, I'm going to ask you to use the equation because I personally thought it was BS. That if we look back at the homework 1 and homework 2 problems, you always use the intrinsic carrier concentration given here, even when the temperature was not 300 degrees Kelvin. So I rectify that error on the exam by making you calculate the intrinsic concentration at a temperature that isn't 300 degrees K, and then plug that in to be able to determine the built-in voltage at another temperature. So it's nothing that you can't figure out by literally going, oh, this is the equation I use for that part, and then this is the equation I use for the next step, that kind of thing. Then there's going to be, so let's see, that's 2. Junction capacitance problem, which we covered in class. So that's 3. Then there's going to be an exponential diode model problem, a ideal diode model problem, a constant voltage drop diode model problem, a rectifier circuit, and a voltage regulator circuit. That's it. That's the whole test. So it's a little bit of literally everything we did. Yes. Uh-huh. Have to do any plotting? The only, so right now, I think, I haven't made it out yet, but the constant voltage drop problem, I think I'm either going to have you guys plot something or have you identify which circuit corresponds to a particular plot. So like we did in class, specifically with the constant. So if we had a diode in parallel with a resistor, in series with a resistor or something like that, you know what the slope looks like and all that kind of stuff. That's as much plotting as it's going to be. So I'm not going to make you do any load line analysis or anything like that where you have to accurately plot an exponential curve and then find where that point intersects with the load line to determine the operating point of the diode, because that is painful. And it would be wildly difficult to make you guys do that in a short amount of time. So yeah, a lot of the problems from the book require that method. Your calculator, by using your calculator to set up, so if you can get the equation of the load line and the exponential model and set them equal, your calculator can solve it without doing all that crap ton of plotting and all that kind of stuff for you. So there will be an exponential model based problem, but it's something that you can use the equation solver on your calculator to take care of without having to do any fancy pants math. Okay, so very, very similar to the example that we worked in class. Okay. In my opinion, and technically, I am going to be asking you to do slightly more than what I did in some of the examples in class. Meaning, I don't remember if we worked a workout problem for drift current or something like that, but it's not particularly hard if I give you the parameters, that kind of thing. It's not going to be anything that you can't look at the equations and be like, oh, this is what I'm supposed to use. And I'm setting up the equation sheet in the order of the material covered in class. So I was actually, when I was working on the test over the weekend, complaining to my wife about how frustrated I was getting because I couldn't make the test hard enough. That being said, I'm also the person who made all those Circuits 1 tests who said they were all too damn easy, and then so many of you did very poorly on it. So I'm not trying to sandbag your grade or anything like that. I don't think any of this material is wildly difficult per se. If you've done the homework, on the examples that we've worked in class, you should be in very good shape. All right. Okay.
Doctor, the bonus quiz not active.
Okay, bonus quiz. I totally forgot to do it over the break, so I'll have to get that put up today, and it'll be either today or tomorrow, and it'll be due, say, Wednesday at midnight or some crap like that. So I'll give you ample time to do it, and you will actually get to do it so that you'll get those bonus points towards the test, for sure. All right? So it'll be, I think, a 15-minute time limit, but I'll let you get to it when you get to it, kind of thing. Any other questions?
Yeah, you mentioned that you were going to give us practice problems because the test that you had looked at, there were a lot of questions. But it sounds like y'all are redoing the test.
Yeah, we're redoing the test entirely because that test was like 28 questions or something like that, and to do 28 questions in an hour and 15 minutes seems ballpark impossible. So we're restructuring pretty much everything. So, I mean, if you're wondering what you're supposed to be studying for, again, drift and diffusion current, built-in voltage, junction capacitance, exponential diode model, ideal diode model, constant voltage drop diode model, rectifier circuits, voltage regulator circuits, which were the topics we covered in order on the 8 days of class we had before the break. So.
It is an hour and 15.
I got to talk to Prashant about that. I would prefer to give you guys, so technically the test is supposed to be as long as a class meeting. And that's coming from the administration above, because there were certain classes where it was like an hour and 15, and not in electrical engineering, where an hour and 15-minute class had a 4-hour test. I think that was a couple of ME professors were doing something like that. And so it came down that if you do, night tests can only be administered when there are multiple sections of a class, so there are 2 sections of this class that we can get away with doing a night exam instead of doing it during the class meeting. And the exam is supposed to be take the same amount of time as the class meeting. I would prefer that you guys had 2 hours to do it. It's not that I don't think you can do it in 2 hours or in an hour and 15 minutes, but I think that that would put undue stress on you guys. So I don't want a test. I'm not designing the test to be 4 hours or anything like that and giving you significantly shorter time or anything. So I'll talk to Prashana about that, and I'll maybe ask you guys, I don't want to get in trouble. I don't want to get yelled at by the dean is my bottom line here. I'm trying to stay off of his shit list as best I can. So I want to give you enough time to take the test, but not so much time that somebody who just drags ass will sit there forever and waste my time, nor make it seem like the test was designed to be taken over multiple class periods, because that's not in the spirit of how we're setting this up. Does that make sense? So at absolute most, it would be a 2-hour test designed to not take you the full 2 hours. So that would just be more time for you to figure stuff out, which again, there's an equation sheet, so it should be pretty straightforward in my opinion. Whatever. All right, any other questions? All right, see you guys on Wednesday for the review session, which I don't know, unless you ask specific questions, I don't know what we're going to talk about, because I will wind up giving you the answers to the test.
That is also okay.
I disagree, only because it's not fair to the other section.